The Lambert ratio tells if u1 plus u2 plus u3 plus to un is a series of positive terms with the nth term n plus 1 term denoted by un and un plus 1 respectively, then let the limit as n tends to infinity of un plus 1 over un be equals to L. If L is less than 1, then the series converges. If L is greater than 1, then the series diverges. If L is equals to 1, the series may converge or diverge. That is, the test is inconclusive. So when L is equals to 1, we are not certain whether or not it diverges or converges by the Lambert ratio talks. Now let's take some example. Example 1. Test the convergence of the series 1 plus 4 over 1 factorial plus 9 over 2 factorial plus 16 over 3 factorial plus 25 over 4 factorial plus to infinity. So this is the series, and we have to test if the series converges or diverges. Now, it's obvious that this series is not an alternative series because all the terms are positive. So we will likely use the Lambert ratio test to test the convergence. But now, let's simplify this series with a summation sign. We just have to observe this series and look for a general rule that we can use to express the series. Now, what would that rule be? Now, 1 is the first term, 4 over 1 factorial is the second term, 9 over 2 factorial is the third term, 16 over 3 factorial is the fourth term, and 25 over 4 factorial is the fifth term. Now consider, the first term, the numerator here is 1, second term, numerator is 4, third term, numerator is 9, fourth term, numerator is 16, the fifth term, the numerator is 25. So that will tell us that we need to square the number of terms to get the numerator. 1 square is 1, 2 square is 4, 3 square is 9, 4 square is 16, 5 square is 25. So it becomes the summation from n is equals to 1 to infinity of n squared. So this solves the numerator. When n is 1, 1. When n is 2, 4. When n is 3, 3 square is 9. When n is 4, 4 square is 16. When n is 5, 5 square is 25. So what about the denominator? Now let's compare. The first term gives us 0. Second term gives us 1. Third term gives us 2. Fourth term gives us 3. Fifth term gives us 5. So we observe that it's as if we are subtracting 1 from the number of terms. 1 minus 1 is 0, 2 minus 1 is 1, 3 minus 1, 2, 4 minus 1, 3, 5 minus 1, 4. So this becomes the nth minus 1 factorial. 1 minus 1, 0, 2 minus 1, 1, 3 minus 1, 2. So this expression here perfectly describes this series. We need to test if the series is convergent. Now, while solving with the Lambert ratio test, we need un. We also need un plus 1. Now for un, the Lambert ratio test works with this expression, the summation from n equals to 1 to infinity of un. So the entire of this expression here is un. So un is equals to n squared all over n minus 1 factorial. So this un, the un plus 1, we are going to substitute n plus 1 in place of n. So n plus 1 all square. There's n here, so we put n plus 1 in place of n. While this n over here becomes n plus 1, then minus 1 factorial. If we simplify this, it gives us n plus 1 all square all over n factorial, because 1 minus 1 is 0. So un is this, and un plus 1 gives us this. So the next step is to find the limit as n tends to infinity of un plus 1 all over un. The limit will determine whether or not the series converges or diverges. So let's proceed. This is the limit as n tends to infinity of un plus 1 is n plus 1 all square over n factorial, which is n plus 1 all square over n factorial. Then this all over sign here, we can use the division sign for it. So all over un, and un is n squared over n minus 1 factorial. N squared all over n minus 1 factorial. So we need to simplify this expression. This gives us the limit as n tends to infinity of n plus 1 square all over n factorial times. Now if we turn division sign to times, we need to take this numerator down and denominator up. So it becomes n minus 1 factorial over n square. So we have the limit as n tends to infinity into n plus 1 square all over n factorial. But simply because there's n minus 1 here, and there's a way we can factorize n minus 1 out of this n factorial. So we have n into n minus 1 factorial. Of course, n factorial is the same as n into n minus 1 factorial times n minus 1 factorial all over n squared. Now this n minus 1 factorial will go with this n minus 1 factorial. So we'll be left with the limit as n tends to infinity all over n plus 1 square into n times n square will give us n raised to the power 3. Okay, so this is the limit as n tends to infinity. If you simplify this numerator, it's going to be n squared plus 2n plus 1 all over n raised to the power 3. So we stop at the limit as n tends to infinity of n squared plus 2n plus 1 all over n raised to the power 3. Now we're dealing with infinity. All we have to do, we'll find the n that has the highest power, multiply through with that n. So it gives us the limit as n tends to infinity of n squared over n raised to the power 3. N raised to the power 3 is the highest power, plus 2n over n raised to the power 3 plus 1 over n raised to the power 3 all over n raised to the power 3 over n raised to the power 3. So this gives us the limit as n tends to infinity. Now if you divide this, it's going to be 1 over n plus, divide this will give us 2 over n squared plus 1 over n raised to the power 3 all over 1. This is equals to, now if we put in infinity into n in place of n, 1 over infinity plus 2 over infinity square plus 1 over infinity cube all over 1. And all of this expression, they are 0. This is 0 plus 0 plus 0 over 1, which is equals to 0, because 0 over 1 is 0. So the limit is 0, L, which is the limit, is equals to 0. And from the condition given, the Lambert ratio test, if L is less than 1, then the series is said to converge. So since L is equals to 0, less than 1, the series is convergent. Example 2. Examine the divergence of the series. So the series here is 1 over 2 times 1. That's not 2.1, it's actually 2 times 1. plus 2 over 3 times 3 plus 3 over 4 times 5 plus 7 over 5 times 7 plus 5 over 6 times 9 plus, keep on going to infinity. So we have to examine the divergence of the series. First of all, we need an expression that will perfectly describe this series. So let's sort out the expression. We know that it will begin from summation. So there's the first time, the second time, the third time, the fourth time, and the fifth time. Now, in the first time, the numerator is 1, second time 2, third time 3, fourth time 4, fifth time 5. So that becomes easy. From n equals to 1 to infinity of n. So the numerator is obviously n. It just follows. What about the denominator? In the first term, we have 2 times 1, second term 3 times 3, fourth term 4 times 5. Okay, let's talk about the first part of it. First term 2, second term 3, third term 4, fourth term 5th. So it's as if we are adding 1 to the number of 10 to get 2. So it becomes n plus 1. So 1 plus 1 gives us 2, 2 plus 1 3, 3 plus 1 4, 4 plus 1 5, 5 plus 1 6. So we have the first part of it. So what about this other 1, 3, 5? In the first term, it's 1, second term, 3, third term, 5, fourth term, 7, fifth term, 9. If you observe, it's as if these numbers are moving in odd numbers. 1, 3, 5, 7, 9. Odd numbers. So for us to get odd numbers, there's a rule for it. In odd numbers, the general rule for it is 2n minus 1. 2n minus 1 will always give us an odd numbers. Now let's see if it works. 2n minus 1. So 2 times 1 gives us 2 minus 1 is 1. 2 times 2 is 4 minus 1 3. 2 times 3 is 6 minus 1 5. 2 times 4 is 8 minus 1 is 7. 2 times 5 10 minus 1 9. So 2n minus 1 work for all numbers. Assuming it was even numbers obviously is 2n. But if it's odd numbers, it's 2n minus 1. So this is the expression that perfectly describes this sequence. So what we need to do next, we're going to check if this series converges or diverges. So from the question, we already told that the series is divergence. We know that already because we are asked to examine the divergence. So we just have to prove that it is divergence. So we need to find un. We also need to find un plus 1. So when dealing with series has the form, the summation from n equals to 1 to infinity of un, which implies that this entire expression here is equals to un. So un is equals to n all over n plus 1 into 2n minus 1. Now if this is true, to get un plus 1, we just have to substitute n plus 1 in place of n. So it becomes n plus 1 into n plus 1 plus 1 bracket 2 bracket n plus 1 minus 1. If we simplified un plus 1 give us n plus 1 all over n plus 2 for the first bracket and 2n plus 2 minus 1. If we simplify further, we have un plus 1 is equals to n plus 1 into n plus 2 bracket 2n plus 1. This is 2n plus 2 minus 1. 2 minus 1 is 1, so this is 2n plus 1. Okay, so we have un plus 1. Now we need to find the limits as n tends to infinity of un plus 1 over un. The limit will enable us to determine whether the series is really divergence. So let's get started. The limit as n tends to infinity of un plus 1 is n plus 1 all over n plus 2 into 2n plus 1. Now this division sign, we can use division sign for it to make it easy for us. So un is equals to n all over n plus 1 bracket to n minus 1, which is n all over n plus 1 bracket to n minus 1. So we need to simplify the whole of this expression. We have the limit as n tends to infinity of n plus 1 into n plus 2 to n plus 1. This division sign will turn it to times. Then we'll take these down parts up and take the up one down. So we have n plus 1 bracket 2n minus 1 all over n. The limit as n tends to infinity of n plus 1 into n plus 1 into 2n minus 1 all over n plus 2 into 2n plus 1 n. The truth is, it will be really lengthy because we need to expand the brackets. We need to also expand this bracket. So we'll take it one after the other. From the numerator, the top part, we have n plus 1, n plus 1 into 2n minus 1. So let's expand this bracket first. We expand these two brackets, then we expand the third one with it. So we have n into n plus 1 into n plus 1, then close the bracket, and we have this expression here 2n minus 1. We're actually expanding these two brackets first. So this gives us n squared plus n plus n plus 1, then 2n minus 1. This gives us n squared plus 2n plus 1 into 2n minus 1. So we have two expressions here. We also need to expand the bracket. Okay, so to expand this bracket, let's use 2n first. 2n into n squared plus 2n plus 1 minus 1 into n squared plus 2n plus 1. Now if we simplify this down, we have 2n raised to the power 3 plus 4n squared plus 2n minus n squared minus 2n minus 1. So we'll take like terms now. 2n cubed. 4n squared minus n squared is 3n squared. Then plus 2n minus 2n is 0. So 2n is out of it. We're left with minus 1. So this is for the numerator, the top part of the equation. The top part of this equation is what we just solved. Now let's solve the denominator. So for the denominator, we have n plus 2 into 2n plus 1 n. So we also need to simplify this expression. So let's expand these two brackets. Open the bigger bracket, n into 2n plus 1 plus 2 into 2n plus 1, then n. So we have 2n squared plus n plus 4n plus 2, then n over here. So this gives us 2n squared plus n plus 4n is 5n plus 2, all times n. So if we use n to multiply the bracket, it gives us 2n cubed plus 5n squared plus 2n. So the denominator gives us this. So actually stopped at the limit as n tends to infinity of n plus 1 into n plus 1 into 2n minus 1 all over n plus 2 into 2n plus 1 n. This was where we stop. Now we have simplified the numerator and the denominator. So we have the limit as n tends to infinity of, for the numerator, we have this expression 2n cubed plus 3n squared minus 1. So let's write it there, 2n raised to the power 3 plus 3n squared minus 1. While for the denominator, we have this expression here, which is 2n cubed plus 5n squared plus 2n. So we're going to simplify this. While dealing with the limit as n tends to infinity, all we have to do is to divide all the terms with the highest power of n. So we have n cubed, n squared, and n. The highest power of n here is n raised to the power 3. So we have the limit as n tends to infinity of 2n cubed over n raised to the power 3 plus 3n squared over n raised to the power 3 minus 1 over n raised to the power 3, all divide 2n raised to the power 3 over n raised to the power 3 plus 5n squared over n raised to the power 3 plus 2n over n raised to the power 3. So we have divided all of the terms with n raised to the power 3 because n raised to the power 3 has the highest power. Now, if we simplify this, we have the limit as n tends to infinity of 2 plus 3 over n minus 1 over n raised to the power 3 all over 2 plus 5 over n plus 2 over n squared. So after simplifying this cancel this, we're left with 2 here. N squared will go into n cubed, we're left with n 3 over n raised to the power 1 minus 1 over n raised to the power 3. So if we simplify everything like that, we end up having this expression here. So at this point, we put in infinity. So it's equals to 2 plus 3 over infinity minus 1 over infinity cube all over 2 plus 5 over infinity plus 2 over infinity square, and this gives us 2 plus 0 minus 0 all over 2 plus 0 plus 0. All the expression that have infinity at the denominator, they are all equal to 0. So this gives us 2 over 2, which is equals to 1. So 1 is the limit, which is hence L is equals to 1. The limit is 1. From the Lamé steps, if L is equals to 1, we can't ascertain whether it's divergence or convergence, then the test is inconclusive. So we can't determine for a fact if it is divergence or convergence. Example 3. Discuss the divergence of the series 8 over 9 plus 11 over 27 plus 14 over 81 plus 17 over 243. And the list keep on going. So the first step, we must find an expression that perfectly describes the series. There's the first term, there's the second term, the third term, the fourth term. And if we observe, in the first term, the numerator here is 8, second term 11, third term 14, fourth term 17. So what can we make of that? Now, if we have a closer look on the sequence 8, 11, 14, 17, we can see that these numbers, they are very close to the multiple of 3. The multiple of 3, which are 9, 12, 15, 18. They're very close to it. 8 plus 1 is 9, 11 plus 1 12, 14 plus 1 15, 17 plus 1 is 18. Now that gives us a clue. It means that if we add 1 to each of this number, we have the multiple of 3. Let's take a closer look. If we need here to be 9, we can use 3 times n. Obviously, when n is 3 is 9. Then minus 1. When n is 3, 3 times n minus 1 will give us 8. So, at the same way, 3 times 4, 12. 12 minus 1 give us 11. 3 times 5, 15. Minus 1 give us 14. So we're very close. Right now we are at 3n minus 1. But if we use n to be 1, 2, and 3, we won't have the answer. So we need to simplify this further. I want 1 to appear here. So this is what I will do. can simplify it to 3 into n plus 2 minus 1. Of course, this is even better. Now let's see if this will work out. At n equals to 1, 3 into n plus 2 minus 1 will give us 3 into n plus 2 will be 3 minus 1, and this is equals to 8. At n equals to 2, 3 n plus 2 minus 1 will be 3 into this will be 4 minus 1 is equals to 11. So this one is better now. So we're getting very close to getting an expression that will work for the numerator. So we are at 3 bracket n plus 2 minus 1. Okay, so we can simplify this. 3 bracket n plus 2 minus 1 is 3n plus 6 minus 1, which is 3n plus 5. So this is the expression for the numerator. So hence, we're going to use the summation from n is equals to 1 to infinity of 3n plus 5 for the numerator. Then the denominator, for the denominator, okay, when n is 1, the denominator is 9. When n is 2, 27, 3, 81, 4, 243. So what can be done? This is the 3 raised to power something. 3 raised to power 2 is 9, 3 raised to power 3, 3 raised to power 4. So we already know that it's 3 raised to power something. If we use 3 raised to power 1 for first term, it's 3, but we need it to be 9. So 3 raised to power n plus 1. I think that would work. So let's find out 3 raised to power n plus 1. So 3 raised to power n plus 1, n is 1, so 3 raised to power 2 is 9. So 3 raised to power 3 is 27. So when n is equals to 3, that's for the third term, 3 raised to power 3 plus 1 is equals to 3 raised to power 4, which is equals to 81, which is this term over here. So this is the expression. This expression here perfectly describes this series. So we have the summation of 3n plus 5 all over 3n plus 1 from n equals to 1 to infinity. So this expression here perfectly describes that given series. So we're going to work with what we have here. We're going to check if this series diverges or converges. Now we need to find two things, which are un and un plus 1. So for un, we know that this is the same thing as the summation from n equals to 1 to infinity of un. So it means that the entire of this expression here is un is equals to 3n plus 5 over 3 raised to power n plus 1. Hence un plus 1 substitute n plus 1 in place of n. So we have 3 bracket n plus 1 plus 5 into 3 raised to power n plus 1 plus 1. If we simplify this, is 3n plus 3 plus 5 into 3n plus 2. And this gives us 3n plus 8 over 3n plus 2. So this is un and this is un plus 1. So let's proceed. We need to find the limit as n tends to infinity of un plus 1 over un. So this is equals to the limit as n tends to infinity. Un plus 1 is this expression here, which is 3n plus 8 all over 3 raised to the power n plus 2. So divided by un, and un is 3n plus 5 divided by 3n plus 1. We need to simplify this expression. So it's going to give us the limit as n tends to infinity of 3n plus 8 all over 3n plus 2 times. We need to swap these two terms. This is 3n plus 1 all over 3n plus 5. So this gives us the limit as n tends to infinity into 3n plus 8 all over. We can simplify this expression to be 3n times 3 raised to power 2 using this is times 3n times 3 all over 3n plus 5. So from here, some terms will cancel out, like 3n will cancel out 3n. Then 3 will cancel out the square. We're left with just 3 here. So we have the limit as n tends to infinity of 3n plus 8 all over 3 into 3n plus 5. So this can be further simplified into 1 over 3. 1 over 3 is a constant here. Then the limit as n tends to infinity of 3n plus 8 into 3n plus 5. We're very close to the answer. At the point what we have now is 1 over 3, the limit of 3n plus 8 all over 3n plus 5. Now we're going to divide all the terms by the highest power of n. The highest power of n is n raised to the power 1, so this gives us 1 over 3, the limit of 3n over n plus 8 over n all over 3n over n plus 5 over n. So this gives us 1 over 3, the limits of 3 plus 8 over n all over 3 plus 5 over n. As n tends to infinity, n tends to infinity, n tends to infinity. So this gives us 1 over 3 into 3 plus 8 over infinity all over 3 plus 5 over infinity, which is equals to 1 over 3 into 3 plus 0 over 3 plus 0 equals to 1 over 3 into 3 over 3. This is equals to 1 over 3 into 1, and this is equals to 1 over 3. So hence, the limit L is equals to 1 over 3. And according to the Lambert ratio test, when the limit is less than 1, this is less than 1, so the series converges. If you want to know more about the Lambert ratio test, or you have any question in any of the tests of convergence, feel free to ask me on WhatsApp. Meanwhile, subscribe to my channel, share and like my videos. I'll see you in my next video.